Hi, I am Immanuel Fink from the University of Konstanz and I present the paper Relocations, Augmenting Personal and Shared Workspaces to Support Remote Collaboration in Incongruent Spaces. This work was done by me, Johannes Zagermann and Harald Reiterer from the University of Konstanz, as well as Hans-Christian Jetter from the University of Lübeck. Several applications exist that enable remote collaboration in virtual reality. In the applications, users are often able to share existing documents or share the screen content of local physical devices in the VR environment. Thereby, the VR applications provide a common spatial frame of reference, supporting spatial awareness, non-verbal communication, and presence. However, VR excludes at least the visual physical environment and therefore also prevents the interaction with co-located users and physical devices in the local environment like paper notes, computers, smartphones, tablets, and other interactive surfaces which have different visual and haptic qualities. With augmented reality, the physical environment is available and therefore interaction with co-located users and physical objects in the local environment is possible. However, in contrast to VR, the common spatial frame of reference is limited. Virtual objects still have a common spatial frame of reference, but they might be out of reach or outside of the local walkable space when, for example, the remote walkable space is larger. Physical objects or devices are available locally, but they may not be available remotely or are not at the same location remotely. This also applies to screens whose screen content is shared. The screens are probably located at different places in the rooms, limiting spatial awareness and non-verbal communication while working with these devices. This problem of different physical spaces has been addressed in previous work using different approaches. Boon et al. Introduced COVA, where the local physical space of an augmented reality user is shared with a virtual reality user, or more precisely, with an augmented virtuality user. While in this approach the whole physical space is available remotely, users have to decide on one physical space, which limits the capabilities for remote users. et al. Developed a technique to position avatars representing remote users in different physical environments depending on the remote user's current position in their local environment. For their placement algorithm, they performed a user survey asking for the preferred avatar position in different situations and environments, identified a set of features, and trained a neural network for generating the plausible position of the avatar. In 2021, they adapted their technique to also enable remote collaboration in front of a screen. In their user study, they mainly focused on technical aspects and general user experience, but did not further investigate how collaboration unfolds in such spaces. In their approach, all features of the physical environment must be defined manually, resulting in a high configuration effort. But when collaborating with remote users, often not all parts of the physical environment are relevant for the collaboration. The previous work inspired us to create a concept that facilitates remote collaboration with multiple personal and shared workspaces relevant for collaboration, using augmented reality to potentially support spatial awareness, non-verbal communication, and presence. To explain the problem of incongruent physical spaces and our solution approach called relocations, we use the example of two co-workers, Paul and Anna, who want to collaborate remotely in their individual offices using two physical devices, a large screen with an online shared whiteboard, red, and a desktop computer for individual activities, yellow. This is a top-down view of the offices and workspaces. When using a global one-to-one mapping to visualize Paul as an avatar in Anna's office and Anna as an avatar in Paul's office, a common spatial frame of reference cannot be established for both collaboration-relevant areas at the same time. Whilst Paul's avatar in Anna's office is also in front of the whiteboard screen, Anna's avatar in Paul's office is not in front of the desktop screen. We introduced the concept of relocations. Relocations are user-defined workspaces whose position and purpose are defined in a setup process. Afterward, every relocation uses an independent local coordinate system in front of the workspace to maintain the common spatial frame of reference. This way, remote users can be represented in the remote space at the position of the corresponding workspace with the same purpose. With this method, Anna's avatar is like Anna located in front of the desktop screen, and Paul's avatar is like Paul located in front of the whiteboard screen. The avatars are located inside the corresponding remote relocation at the same position as the users in their own local relocation, imitating their orientation and movements. Remote users are only represented as avatars inside relocations. When a user leaves a relocation, the avatar fades out at the remote site. When a user enters a relocation, the avatar fades in again. The relocation concept also allows to provide additional awareness cues like gaze rays within and across relocations. When Anna rotates towards the whiteboard screen, the one-to-one mapping of the rotation will be interrupted and her avatar rotates towards the whiteboard. The gaze ray of her avatar points to the same spot on the whiteboard she is looking at. The same behavior also applies to Paul when rotating towards the desktop screen. For the exploration of the concept, we developed an initial prototype using the Microsoft HoloLens. In the setup process, the screens in the rooms are calibrated by holding a calibration marker on the corners of the relevant screens. Once set up, users can look at a room marker to load the configuration of the room. Afterward, they can hear each other and when inside relocations also see each other as a 3D avatar imitating position and orientation. The integrated voice chat uses the spatial audio functionality of the HoloLens to play the voice from the avatar's direction. A green line visualizes the head gaze of the remote user. Our initial relocations prototype also supports 2 relocations. Here we see 3 example scenarios from a third-person view. On the left, both users are inside the same relocation in front of the desktop screen. In the middle, the users are inside different relocations. The user in room 1 in front of the whiteboard screen and the user in room 2 in front of the desktop screen. On the right, we see an example for the gaze visualized across relocations. The user in room 1 is inside the whiteboard relocation and looks at the desktop screen. Therefore, the avatar in room 2 interrupts the one-to-one mapping and also rotates to the local position of the desktop screen. We conducted an exploratory user study to investigate the relocations concept with the initial prototype and answer our research questions. We were interested in 2 main topics: the collaborative behavior of the participants and their perception of presence. To study collaborative behavior, we manually coded the collaborative activities using the well-established coupling styles. Additionally, we also coded participants' individual behavior such as their spatial locations, viewing directions, or deictic gestures. To understand the participants' perception of presence, we utilized the Common Temple Presence Inventory questionnaire. Furthermore, we conducted a semi-structured interview at the end of each session and complemented our data collection with spatial temporal data. We invited 16 participants forming 8 dyads to participate in our exploratory user study. 2 labs at the University of Konstanz served as distributed work environments for our participants. Both labs were facilitated with a personal and a shared workspace. The personal workspaces were represented each by an office desk and a desktop computer with screen, mouse and keyboard. The shared workspaces were represented each by a 65-inch multi-touch display mimicking a digital whiteboard. The individual positions of the workspaces were different in the labs to study the main purpose of the concept, enabling remote collaboration in incongruent spaces. The workspaces in Lab 1 were arranged in an L shape and the workspaces in Lab 2 were placed back to back and had an offset. All relocations had the same size. Participants were welcomed in the corridor by 2 examiners and separately brought to one of the 2 labs. This prevented participants from spotting any difference in the study environments. In the study setting, participants had to perform an adapted version of the hotel search task by Jetter et al. Here, participants have to agree on a hotel for their vacation. However, each participant has a different set of personal requirements. The task is designed that a simple combination of all requirements does not result in a solution. Those participants have to negotiate, discuss and ponder their personal requirements. At the personal workspace, the desktop screen, participants had a custom website with a list of all hotels and their attributes, in the look and feel of a state-of-the-art hotel booking website. Here the screen content is not synchronized between the rooms. At the shared workspace, the whiteboard screen, participants worked with a different view on the same data. Here all hotels were represented as sticky notes with their name and image. The positions of the sticky notes were synchronized between the rooms. The overall goal of our user study was to understand how relocations can facilitate remote collaboration in incongruent spaces. As part of the concluding interview, we asked participants if they noticed that their spaces differed in their spatial layout. 15 of 16 participants did not notice that their room layouts differed. This shows that the general idea of relocations worked at least for our study environments. When leaving a relocation, avatars became invisible. This was a design decision to reduce visual clutter and unnatural avatar movements which might evoke an uncanny valley effect. Interestingly, in the interview, 10 of 16 participants did not notice that the avatar was not visible all the time. However, we are aware that in reality, room layouts might differ more, and larger distances between relocations could lead to a reduced spatial awareness when collaborators are outside or between relocations. To better understand the collaborative activities while using our prototype, we coded them based on established coupling styles. The most frequent coupling style in our analysis was SIDC, which was previously documented for co-located and remote collaboration. SIDC means sharing of the same information but using different physical displays for coordinated exploration. In our study, we further distinguish between participants looking at different screens, the situation presented at the top, and both participants looking at the individual desktop screen, the situation presented at the bottom. For the first case, we did not observe behaviors that usually only occur during co-located collaboration. However, when both were looking at their individual desktop screen, we observed participants in several situations not sitting down but standing next to the chair at the desktop screen, as the chair was virtually occupied by the remote participant. This is interesting as it imitates natural spatial and social relationships between local and remote collaborators that are typical for co-located collaboration. We were also able to observe the coupling styles VE and SV that were only documented for co-located collaboration so far. VE means view engaged. Participants were working on different screens while one was working at the whiteboard screen and the other was sitting at the desktop screen. Interestingly, the participants at the desktop screen verbally guided their team partner or even used didactic gestures to indicate where they would position a sticky note. The content of the whiteboard screen was synced and therefore allowed participants to catch their partner's attention without relocations. However, we also observed situations in which participants commented on the behavior of the remote participant without interaction at the whiteboard. The coupling style SV means sharing of the same view. Both participants were standing in front of the whiteboard screen and manipulating the sticky notes cooperatively while sharing the same view. Here participants benefited from both the awareness cues provided by the relocations like the gaze ray and spatial sound, as well as by the synchronization of the whiteboard screen. Therefore, findings cannot be clearly attributed to the relocations alone. The coupling styles view engaged and sharing of the same view were only documented for co-located collaboration so far, indicating that the relocations to some extent bridged remote and co-located activities. This is also reflected in the results of the TPI presence questionnaire, where participants in general indicated a sense of social presence and social richness. Also in the interview, 12 participants mentioned they felt as they were in the same room. Spatial presence seems to be a topic for future research, as the questionnaire ratings on the perceived sense of spatial presence have a wide range. However, 13 participants mentioned during the interview that they always knew where their team partner was, which indicated some sense of spatial presence. Also, observed situations in which participants stood next to the chair while it was virtually occupied indicate a sense of spatial presence. If you're interested in more details, please refer to our paper. You can also find relocations as an open source project on GitHub. Thanks for listening.